Okay, so we continue the travel in the solar system. So we were at Phobos, and I would like to tell you one particular observation that we did in 2011, which was very special. It's this one. So you remember the Phobos is in the circular orbit in the equatorial plane. We have the elliptical orbit of Mars Express, and I forgot to mention its elliptical and polar orbit. So, and the condition of both makes that we can meet Phobos also regularly. So Phobos circular and equatorial, Mars Express elliptical and polar, and the mix of two makes that we meet regularly. One particular outcome of all the Phobos observation is that we could measure with much more accuracy the position of Phobos. Because you know, all the bodies, they move in the solar system, and what is important to know is the position. Because of course we don't want to collide, we don't want to crash, and we want to observe them at the right time. And the position of all the bodies, they are known to a certain accuracy, of course. And in the case of Phobos, before the start of Mars Express mission, I don't know if you have an idea of the inaccuracy in the position of the orbit. I don't know, what would you guess? At which accuracy do we know the position of Phobos? I don't know, it's something that you know.
2 kilometers?
That's a good number, that's the number we have now. Okay. But before the mission and even at the beginning of the exploration of Phobos, it was something like 20, 30 kilometers. And with such an inaccuracy, it's difficult to make precise measurement. But with all the observations of Mars Express, we managed to really reduce the uncertainty. And then we managed to have a special observation which was this one. So Mars Express was there. It was in, you see, June 2011. So we imaged Phobos. Phobos is here, so at 11,000 kilometers from Mars Express. And given the very precise position of Phobos, we could predict that if we switch on the camera at that time and if we point the spacecraft there, in the background, we should see Jupiter. This is what we try. And in fact, we tried before, because Mars Express was in orbit since beginning of 2004, and at the beginning we failed because the orbit was not precise enough. And in 2011 we say, okay, let's give it a new try now that we improved the knowledge in the position of Phobos. And then we try that, and then again we got the data, and we see we got the data on the computer, and we see what's going on. And in that case it was successful, as I will show to you, because we had Phobos, and we had Jupiter here, and then a few seconds later here, and then a few seconds later here. It was even a kind of occultation in that case. So even this very precise, first, because of the precise orbit determination, we can do that. It's quite interesting because we can confirm the accuracy of the position of Phobos. And in addition, because of the precise measurement, and you see here Phobos is at its exact location, we can even improve what we call the ephemerides. And for many scientific questions, it's good to know the position of the moons. In particular, if we want to understand the origin of the moons, it's very important to know their orbit. I can answer a detailed question about that later, but that's a complete topic on its own. So, but it's quite an interesting topic. So that's what we did. So I tell you now it's Jupiter, but do you believe me that it's Jupiter? I don't know, I tell you. Do you think it's Jupiter? Yes? Because I tell you that it's Jupiter. So now I will zoom on this, yes, to make sure it's Jupiter. Because some of you, I see you have some doubt. So this is Jupiter, yeah? And even interesting, but in this screen it's always difficult to see, but we see the three Galilean moons also. I think it's on my screen, but here I know it's a bit difficult, but if you find the images on the web, there is one here, there are two here, and the other one I think it's somewhere here. But we see the Galilean moons, even from Mars Express orbit with a camera which is more than 20 years old, so it's not, it's a good measurement, I think. So before I move to another topic, I just would like to mention this interesting encounter. I don't know if you heard of it. It was, so this is Mars. So it's taken from Earth with a big telescope. You see the star background here. So this is Mars, a bit overexposed. And here this is the comet, which is called this like that, so siding spring, okay. And I don't know if you know the story of this comet. I don't know if you heard of it. Did you heard about this comet? No? Yes? So that was a very, very interesting event that happened. It was in October 2014. So the comet was identified in 2013. It's the comet that we didn't know before. And when the comet was identified, there were orbit determination to see where the comets come from and where the comet is going, just to know what is the trajectory. And people find that the comet will go extremely close to Mars in October 2014. And even at the time of the discovery, there was a risk of collision of the comet with Mars. So people were very excited because a collision, imagine a collision of a comet with Mars. That would have been just fantastic to see with the orbiter and to see the big event. Now they were after many additional observations, and the trajectory was refined. And unfortunately, there were no risk of collision anymore. But the closest approach from with the comet to Mars was this distance, for example, was 1/4 of the Earth-Moon distance. So it was still very close. So that's why it was an interesting event that we have observed with the Mars camera and other Mars data. That was very interesting. Also, that could be a topic of its own, a 1-hour conference. I will not go into much detail. But that I wanted to tell is because that was a very special event, and with the comet, you have a lot of dust grain with the coma. And in fact, that was a threat to the Martian orbiter, because we were scared that we could get some impact on our satellites, and an impact on the satellite, it's never good. So that's why when we know that, we had 1 year to prepare the best strategy how to protect the orbiters during this encounter. So there was also a lot of work behind, and we changed the orbit to make sure that at the time of the closest approach, we were a little bit behind Mars to be protected from the dust impact, this kind of stuff. So there were a lot of interesting technical activities. And then during the closest approach, also some instruments were switched on, and we got some interesting measurement of how the dust interact with the atmosphere of Mars. But that's another topic. So given time limitation, I think I will go directly to JUICE, because that's my next project. So JUICE, the next large mission of ESA to Jupiter. JUICE means Jupiter Icy Moon Explorer, and that's a mission to observe Jupiter in details, and also in particular 3 icy moons around Jupiter. And I will tell you why it's interesting. There are two main targets of the mission. The first one is this one. I'm pretty sure you all know what it is. Europa. So Europa, one of the Galilean moons of Jupiter, very interesting, because when you see the surface, there are also, from the geological point of view, some striking features. It looks like a very smooth surface, like a real nice ball. Not many craters, as you can see. So that means something about the edge of the surface, as we discussed, and also the activity. Young means also active moon. All this orange pattern, there are some material from the surface that is probably non-ice, maybe organic material. We would like to find out more. And past mission, in particular from NASA, they have indicated that there is some evidence of liquid water below the surface. Like for Enceladus, where I show you there is a global ocean, we suspect we have strong evidence of liquid ocean also under the surface. And again, liquid ocean, always interesting for habitability point of view. So that's one of the main targets of the mission. The second main target is this one, maybe less known. I don't know if you know what is this one. No, it's not Callisto. Ganymede. So Ganymede, very interesting. It's the largest moon of Jupiter, and also the largest moon in the solar system, a little bit bigger than Titan. So big body, that means a lot of things to explore, very interesting. And you see the surface is also different from Europa, but quite interesting. A lot of different geological features, craters, these kind of features here. And from what I've told you on Mars, looking at the surface, we should be able to derive the history of this moon. Because when you look at different places, you can really derive what happened in the last 4 billion years. So Ganymede, very interesting body from the geological point of view. Similarly to Europa, we suspect that there is also liquid water under the surface. So it's quite fascinating that you look at this body and there is an ocean under the surface. I don't know if you find the things interesting, but I think to me it's quite fascinating. And there are some ideas that there is even more water here than on our own planet. So that's quite interesting. And the third interesting aspect of this moon is concerned the magnetic field. Because if you consider solid bodies like the terrestrial planets, Mars, Venus, Mercury, there are only 2 planets, solid planets, which possess a magnetic field. And I guess you know it's the Earth, and the other one is, maybe you know or don't know, I don't know, Mercury. Mercury, you have a magnetic field on Mercury. And the third and only one body, otherwise it's Ganymede. So it's always interesting to study magnetic field because magnetic field is an important part of a planet. For example, it protects the Earth from solar wind input and so on. So we have a magnetic field, an internal magnetic field inside Ganymede, which is interesting to study. And this magnetic field is embedded in the large magnetic field of Jupiter, because Jupiter as a gas giant has also a large magnetic field like Saturn. So we have a small magnetic field inside a large magnetic field, plus you have the ocean inside, which contains some particles like dust or salt, which conduct the electricity. And that means when there is a liquid which conducts the electricity, you can have a third magnetic field, which is called the induced magnetic field. So from the magnetic point of view, it's quite an interesting target. So that's why we go there with JUICE. And just to put the things in perspective in terms of size, so different planets and moons. So you have the Earth here, and you see for Jupiter the size of the Galilean satellites. So Ganymede is the largest one. So Callisto, it's also a big body. Europa is more like our own moon. So you see, Io it's also a very interesting moon. It's like our own moon. So you see Jupiter is quite interesting with 4 large moons, while for example Saturn, only Titan is a large moon. So that makes the system of the Jupiter satellites very interesting to study. And with JUICE we'll study mainly those 3. And because first, from the trajectory point of view, they are accessible to the mission. It's a bit difficult to go to Io for many reasons. And also because, as I said, on this moon we think there is an ocean. This one, and Callisto, also we believe there is also an internal ocean inside Callisto. So that makes the whole system very, very, very interesting. So this is what I just said. So for Europa, this is what we think the interior is made of. So we have the icy crust here, the interior with the core, and you see here the possible liquid ocean here with a question mark, which is in a direct contact here with the volcanic seafloor. So that's from the habitability point of view. It's quite an interesting, and we would like to know more. So during the mission, we will have 2 flybys of Europa. We cannot have more flybys of Europa because Europa, as you have seen in this chart, that's the distance to Jupiter. Europa is relatively close to Jupiter, and the closer we have to Jupiter, the more dangerous it is for the spacecraft because of radiation. Because of the large magnetic field of Jupiter, there are a lot of charged particles, very energetic, and when they hit any spacecraft, it can damage electronics, cameras, and so on. So that's why we cannot go to Io. Europa will do only 2 flybys, and then we'll concentrate on Ganymede and Callisto, just because we want to have a spacecraft in good health for most of the part of the mission. Also, another interesting aspect of Europa will be to really study the ice crust in details, because we think there is also a possibility to have liquid water pockets here, just below the surface. And with our radar, we have a radar on board, which we will try to probe the few kilometers here below the crust and to try to find interesting feature like liquid water just below the surface. That's the goal of the mission, one of the goals of the mission. I will come back to that to the, I have the trajectory, but for Ganymede, there will be something like 13 flybys, but the most interesting part will be at the end of the mission, we will orbit around Ganymede. So for Europa, there will be 2 flybys, Callisto something like 10, 13 flybys. Here, again, 12, 13 flybys, and then orbit around Ganymede. Another interesting aspect of Europa is that it's very similar to Enceladus. Well, Enceladus, you have seen the water plumes. You remember that? We suspect the same similar processes at Europa. Also, there is less evidence, but there are some observations of the Hubble Space Telescope, which has indicated evidence for geysers or water vapor ejection from Europa, but they have not been confirmed yet. They have just been seen only a few times. So that's why, but there is a possibility that we have similar processes at Europa than at Enceladus. But that's something that hopefully we will detect and confirm and study in more details. For Ganymede, that's a snapshot of the interior. And again, that's a very interesting moon because it's highly differentiated. You see the iron core, the mantles. This is the crust here, ice, and then in between an ocean again. So that's what the modeling of the interior tells us, based also on some measurement from previous mission, which are at the limit of sensitivity. So this is, we have evidence, but we need clearly a confirmation of that and to study this ocean in more details. And the fact that it's a saline ocean, it's important because if it's only pure water, we'll not have any magnetic field information because there is no conduction of electricity. If there is a salt to conduct the electricity inside, we should be able to see disturbances in the magnetic field, and that's a very powerful way to detect an ocean. The tricky thing is, you see the ocean is below the crust, and there is no way, we are not going to land on the surface and to make a hole of a few kilometers to find where the ocean is. It's just not possible. So we have to rely on a lot of indirect measurement, like magnetic field and other measurement. But all these measurements, even if they are indirect, if they are all made together, they should constrain the interior and tell us something about that. So, but because we cannot go there directly, so that's as easy as it is. This is what I was saying for the magnetic field. So that's an illustration of the magnetic field lines around Ganymede. And you see it's quite complex because, as I said, there is an internal magnetic field, the dynamo of Ganymede. There is an external magnetic field of Jupiter. And there is the change of the magnetic field due to the internal ocean, which makes the complete picture very complicated. So people who will analyze the magnetometer data, they will have a tough job to really characterize everything, to see what is the exact signature in the magnetic field data due to the internal ocean. But, that will be possible, but that's a difficult measurement. Another measurement that we'll be doing to study the interior of Ganymede is this one, and that's a very interesting one because so that's Ganymede, and that were some observations again of Hubble Space Telescope. And if you see this image, what does that tell you? What do you think they are, those light emissions at Ganymede? Yeah, exactly. So that's our on Earth. We have aurorae, like you know, on Earth the auroral oval due to the internal magnetic field. Because Ganymede possesses also its internal magnetic field, we have also aurorae. So that's first one very interesting measurement to be done. But the most exciting part is that because of the ocean, the magnetic field will change, as I said, and then the location of this aurorae will change with time. So that means if you observe aurorae and if you do a temporal evolution, if you see from the oval, oval will move with time, then you can relate those movements to the interior of Ganymede and the internal ocean. And that's, if you think about that, it's quite a complex measurement, but that links overall physics, so people doing electron bombardment, plasma physics, which people who study the interior of the moon, and normally those two communities, they are completely disconnected because there is not something as extreme as studying the interior of a planet and the plasma of the planet. And in that case, we'll combine these two approaches. And that's when I said that when we sell a mission, we want to address, we want to serve different communities. This is the best example of serving the community doing plasma physics, so charged particles, electrons at 80 kilometers altitude, with people studying the interior of a planet. I've never seen that in any other mission. So just to give you the interdisciplinary aspect of the mission. Callisto also interesting because when you look at the surface, it's completely different from Europa and Ganymede. When you look at that, craters everywhere. So that means the history of Callisto is also different from the history of Ganymede and Europa. And because we want to compare what's going on in the Jupiter system, it's good to study Europa to understand what's going on, to study Ganymede to understand, and to understand Callisto. And Callisto is probably, when you look at this crater density, it's probably a very old object that not much happened in the last billion years, while the other two, Ganymede and Europa, they are more active. And we want to understand why in the same environment of Jupiter, we have active worlds and more worlds which are more dead, so to say. So that's also interesting. Jupiter, because we are in orbit around Jupiter, we'll study the atmosphere. I mean, we will spend more than 2 years in orbit around Jupiter doing flybys, but when we are not doing a flyby of the moon, we'll point the instrument to Jupiter, and we have spectrometers, images to study the planet in details, the circulation, the great red spot, and so on, the aurora here. So that we will do also a lot of Jupiter science. And also it's important to study Jupiter as a whole system because we want to understand what are the conditions for the moons to have to harbor internal ocean inside. So why do we have an environment that allows to have this kind of habitable place in the Jupiter system? So for that we need to study Jupiter as a whole. And plasma physics around Jupiter, because Jupiter has a large magnetic field which rotates very fast, because Jupiter rotates very fast in 10 hours. So if you compare with Earth, 24 hours, a small planet, Jupiter, a big planet, rotating at 10 hours. So that means there is a fast and very strong magnetic field rotating. So that's interesting to study. And the moons, they are orbiting Jupiter. So they are also in this environment. And we want to study how the magnetic field and the radiation affect or interact with the moons, because that's also important for habitability and things like that. For example, we will expect that the moons, they are really impacted by a strong radiation, so we should see the effect on the surface. The surface should be different whether there is a constant bombardment or not. This is what we call the space weathering, and it's also important to study. So you see the strong coupling between the magnetic field and the moon. So in the case of Io, we'll study that from far, because as I said, we cannot go much closer to Io. But Io, it's a very interesting moon because it's a volcanic moon. So with the volcanic eruption, we inject some plasma into space, and the plasma, they are taken by the magnetic field of the planet. So there is a very strong interaction between the Io and the magnetic field, and in fact some of the plasma content of Jupiter is because Io ejects some ions due to volcanic activity. So that's an interesting aspect here. For Europa, we'll study the radiation, and also because of the internal ocean, there will be an induced magnetic field to study. And as I said, Ganymede, the same, induced magnetic field due to the ocean, plus this mini magnetosphere, mini dynamo within this big dynamo. So it's for plasma physics, it's also a field of interaction that we can be busy for the next 20 or 30 years. That's absolutely no problem. It's quite interesting. The aurorae we will study. That's the aurorae on Jupiter. They have been studied before, but we will continue this to understand the interaction of charged particles with the atmosphere. And if there will be no moons, there will be only one auroral oval, like on Earth. But because the moons, they are linked to the magnetic field and the plasma lines, they also inject particles, and we see in fact the spot of the moon in the aurora. So we see the aurora here, the spot due to Io, the spot due to Europa, the spot due to Ganymede. And that it illustrates the fact that the moons, they are not just moons orbiting Jupiter with no interaction, but they are linked to Jupiter with invisible link, which is the magnetic field. So that's also interesting to study. And just to give an idea of the size of the bodies we are talking about, because that's really big. So that's, if you see from Earth, you look at the stars, you look at the moon, so full moon here. And if Jupiter will be here, so you will see the bright Jupiter. But just to give you an idea about the size of the magnetosphere, that will be the size on the sky. So it's the size of the magnetosphere is larger than the size of the moon. So if you, in particular at this moment, you can see Jupiter and other planets aligned. I don't know if you have seen that. You have Mars, Venus, even Mercury. So, and if you look at the moon and if you look at Jupiter, imagine the size of the magnetosphere of Jupiter. That's larger than the size of the full moon. And another view of that is if you look at the here trajectory, you have the Sun, you have Earth, you have the orbit of Jupiter, and you have the orbit of Saturn. So that's the magnetosphere of Jupiter. And you can see that the magnetosphere of Jupiter goes beyond the Saturn orbit. So that's also quite interesting to note. It's really a large object. So that just gives some information on the size of what we are talking about. So the spacecraft, it's a very interesting spacecraft, a large spacecraft, 5 tons that will be at launch. So that's the main body of the spacecraft. So the instrument will be there. You have also some booms due to antennas. So at the moment, because we start the implementation phase with the industry, everything is on paper. We have no real spacecraft yet. But we have a lot of drawings and things like that, and we are studying the position of the instrument, if this is all right. We are studying the booms of the radar and so on. And one interesting aspect of the mission is this, the solar panels. They are quite unusual because you will see with this, if you build the Rosetta spacecraft with what I gave you this morning, you will see how big are the solar panels of Rosetta. They're already big. You have seen that. Everyone knows that the solar panels on Rosetta, they are very, very big. And on JUICE, they will be twice bigger. Because we are very far, we need to have power at Jupiter. And we have the solar array with 5 panels here and 5 panels here. And the total size is 100 square meters. So there will be 100 square meters of solar panels for the JUICE spacecraft. So I think that's a kind of challenge in itself. And the overall mission profile is also quite interesting because we'll do different flybys, orbit insertion. So here I think it's important that I list to you what will happen. So we plan to have a launch in May, June 2022. So that's the plan. And then I will show you how we go from Earth to Jupiter. We cannot go in a straight line because of celestial mechanics and mass of the spacecraft and rocket performance. So it will take 7.5 years to go from Earth to Jupiter. I will show you how. So that means in October 2029 we will be there. We have the Jupiter orbit insertion. Then there will be several orbits with Ganymede flyby. But then the most interesting phase next will be 1 year later. There will be the 2 Europa flybys. Then there will be a very interesting phase for 6 months. I will show you on the trajectory. We will incline the trajectory because the trajectory will be mainly in the equatorial plane to study the moons. But at some point, we will change the inclination to look at higher latitude on Jupiter. Because like for Mars Express, it will be better to have a polar orbit because with a polar orbit, you see everything because you go over the pole. If you only have an equatorial orbit, you see mainly the equator. And we would like to see many areas on Jupiter. So at some point, for 6 months, we'll incline the orbit. Then we go back to the equator, and after 2 years, there will be we enter in orbit around Ganymede. And then the last part of the mission, less than a year, will be in orbit around Ganymede. So you see from this already that all the time there will be something very interesting from the trajectory point of view. So let's see if it works. So this is the trajectory of the cruise. It's always interesting to see how we send a spacecraft to its final destination. So this is the Sun, this is the orbit of Mercury, this is Venus, this is the Earth, this is Mars, and Jupiter will be someone here later. Yeah. So we launch here, and on Earth in May 2022. We would like to go directly to Jupiter, but it's not possible because the spacecraft it's 5 tons, and we use Ariane 5, which has some limitation. It's a very powerful rocket, but we want to send 5 tons to Jupiter, and we cannot go directly. We don't have enough energy. In fact, NASA is working on a very powerful rocket, which is called SLS, and if they manage to build the rocket and to use it for that, they will be able to go directly to Jupiter, which will take, in that case, 3 years. But for us, we do a little bit of turning around, and it takes 7.5 years. But the important is to go there. Yeah. So before going there, we will use the planet to get some energy with the different flybys. Every time we fly by a planet, we get a little bit more of energy, and at some point we will have enough energy to go to Jupiter. And I will show you how we do that. So first flyby of the Earth there. So we fly by the Earth, we get a little bit Venus here, another flyby. Then the second turn around the Sun, another flyby of the Earth, followed by a flyby of Mars. Hop. And then the third turn around the Sun. So Jupiter will arrive here. We'll have a final flyby of the Earth. You will see it's now, and then we have enough velocity of energy to reach Jupiter, and we will arrive there after 7.5 years. So we have to be patient, and then we will switch on the instruments sometimes like 6 months before arriving to study Jupiter, and then there will be the orbit insertion there. So that's the plan. Yeah. So we have to be patient, and once we are there, so let me check. So that's a long movie. I don't know if we can switch off a bit the light. Okay, so this movie you can I will make sure you get the link to that, because it's going a bit fast, so it's not always easy to see everything. But that's based on the real trajectory of the spacecraft that we have studied so far. So you have Jupiter here and the 4 Galilean moons. So we have Io, Europa, Ganymede, and Callisto. So you will see they rotate quite fast, and this is the JUICE spacecraft orbit. And the first orbit, so here we have to realize that we are already in the Jupiter system. We just had the orbit insertion. And the first orbit, as we said before, is always very elliptical. So the first one will be very long, and then we'll do a maneuver and flybys such that the orbit will be reduced, and then there will be multiple flybys here, and that I will try to show you with this movie. So this is the first orbit. So during the first orbit, we will not do that much because we are really far from Jupiter, and we will be testing if the spacecraft is healthy and so on. But at the end of the first orbit, we'll fine-tune the trajectory such that we have a Ganymede flyby. At the end of the first orbit, we encounter Ganymede here. So that will be in fact the second Ganymede flyby of the mission. Then there will be another orbit, and at the end of this orbit, there will be another flyby of Ganymede. So that's the second orbit. You see now it's closer to Jupiter. too late again. But here we had another Ganymede flyby. So you see orbit and flybys of moons when we can. Then the third orbit. And then, here I was more lucky. And here you see we'll meet again Ganymede for another flyby. So that's always the case of the mission. Every time we are close to the moon, we'll try to have a flyby of the moon. So when we are here when we are close to Jupiter here, we observe Jupiter. We also do some plasma measurement and remote sensing of Jupiter in that phase when we can. And when we meet a moon, we do a flyby, and then we switch on all the instruments dedicated to this particular flyby. So the first part, there will be only Ganymede flyby, and then after a year, there will be some Europa flyby, and here it starts to be a bit complicated to follow because everything is rotating very fast. But at some point, there will be 2 flybys of Europa around this time. And then, as you can see, we are in the equatorial plane of Jupiter because we want to study the moons, and the moons, they are in the equatorial plane. But as I said, at some point we want to escape from this plane to see more different areas of Jupiter, in particular at higher latitude. And for that, we'll use the Callisto flyby, so one of the moon, to change the trajectory of the spacecraft and to escape the plane of the equator and to be at higher inclination. So this is what I'm going to show now. So every time there is a Callisto flyby, it's being used to change the inclination, and you see that the inclination change. And here we can see Jupiter under a different angle. And that's interesting for remote observation, plasma physics, and so on. So we'll stay a few weeks at this inclination of something like 20 or 30 degrees. And then at some point, because we want to continue to study the moons in the equatorial plane, we use again Callisto flyby to come back to the equatorial plane. So this phase will last something like 6-7 months. So now we are back almost to the equatorial plane. And then because at the end of the mission we want to enter into orbit around Ganymede, we have to have a velocity compatible with the Ganymede orbit insertion. It's like Rosetta, we change the trajectory such that we are close and close and at the right speed to meet the comet. And here we want to be at the right speed to meet Ganymede. So for a year, there will be multiple orbit and flybys of moons to make sure that the velocity is such that we can get into orbit around Ganymede. So you see different orbits. So it starts to be a bit messy, but that's how it is. So Ganymede is this one. So I've lost the spacecraft now. So it's here. So you see now the orbits are closer and closer to Jupiter. We are close to the circular orbit. Oh, another one here. Another one here, closer to Jupiter. And then at some point we will be in orbit around Ganymede. So you will see soon. Another orbit closer to Ganymede. And then at some point we will follow the Ganymede orbit, which is there. So now we are in orbit around Ganymede for the last part of the mission. That will be the most interesting part, I suppose. And then at the end we will crash on Ganymede, most likely. And at the end you see all the different orbits. So we'll have something like 50 orbits around Jupiter, 25 flybys. So for 3 years it will be a very interesting mission like Rosetta. Every month something to tell, new images, a new result, and so on. And this movie you can find on the web. So, and around Ganymede, there will be a special orbit. So again, now I think you know that when we enter into orbit around a planet or a moon, it's always elliptical. So the first orbit around Ganymede will be elliptical. It is called GEO, Ganymede Elliptical Orbit. So there will be something like that. Then there will be some trajectory correction maneuver to have a circular orbit at 5,000 kilometers. then the orbit evolution is such that we go back to another elliptical orbit. And then the last part of the mission will be a circular orbit very close at 500 kilometers. And that will be, sorry? Yeah, that will be a polar orbit, yeah. Because here there will be mapping, radar, laser altimeter, and so on. So, and if we have enough fuel, and depending on orbit characteristic, we may want also to go down even at 200 kilometers. That's something that we have studied, but because of fuel limitation, at the moment the baseline is only the final orbit at only 500 kilometers, but we hope to be able to go down. And at the end, most likely, when we run out of fuel, depending on the orbit characteristic, the spacecraft may crash on Ganymede, but that we are allowed to crash on Ganymede. And anyway, at the end of the mission, given the radiation environment of Jupiter, we have to see in which situation is the spacecraft, because it might be damaged or whatever. We take all the precaution to make sure is protected from the radiation point of view, but after 3 years in the Jupiter system, we have to see how the spacecraft looks like. So about the budget, I wanted to have one slide on it, because as I said in the introduction, when I give some talks, in fact, I am often asked the question, but why are you doing all these activities? How much it is? Is it worth the budget? It's something I really get. So I wanted to give you some numbers, and then you can judge by yourself whether those budgets are worth the money, reasonable, not reasonable. So for medium class mission like Huygens, Mars Express, and Venus Express, it's what we call a medium class mission, and the budget is something like 350 millions of euros. So if you consider those missions were selected in late 90s, beginning of 2000, so if we consider that we have something like 350 millions of European, because we are talking about ESA and the European, that means €1 per European spent for each of these missions over 10 years or even 20 years in the case of Huygens. So that's basically because it's on public money and everybody pays income taxes. For this mission, it's equivalent to €1 per person for each of the missions. For Rosetta and JUICE, there are bigger missions, which we call a large mission, and it's more than it's around 1 billion. So that means €3 per person. Now we have more European, so maybe it's €2 per person. So when you pay taxes, you have to say that you give €2 for JUICE and you gave €2 for Rosetta. And when you see the result of those missions, I think, at least to me, we spent well the money. Because in fact, if you compare to other expenses or whatever, I think it's not much at the end. So that means the industry, the space industry in Europe, I think it's quite efficient in making good product and making good missions, and then we got good result. For the annual budget of ESA is 5 billion. So again, that covers all the activity, not only science, but Galileo, the launcher, the International Space Station. And for every European, again, if we come back to what you give to this activity, that's something like €10. So that means one ticket of a movie. So when you go to movie, you give €10, and that's exactly the same that you give to ESA. So every year you give €10 for all these activities that we are doing. So I think it's not bad. And the annual budget of the ESA science program is only 10% of that. So we are working with 500 million euros. So I think that gives the things in perspective, that in fact, it's not when people say, oh, you should invest this money somewhere else, sure. But in fact, it's not that big if you compare to other expenses. I didn't want to give all the other written expenses in other area, but I mean, you can check everything else. I mean, the budget of the European Commission, for example, it's something like 200 billions per year. So it's only a small part of the public expenses in Europe, and I think it's, to me, it's worth the money. So, okay, so I come back now because I have a bit more time. Because I didn't know if I would have time to do that. I wanted to discuss about Venus, because Venus is also an interesting planet, and it's not as well explored as Mars now, because now all the missions, they want to go to Mars to find life, to study habitability, etc. But Venus, it's also a very interesting target, and in 2005 we launched Venus Express, and you see here a beautiful picture just the day before launch from Baikonur with a beautiful sky. So that's a Soyuz launcher. And Venus Express was a special program because it was based on how to reuse the Mars Express spacecraft to have a similar mission. And there was a call for ID, again, as I mentioned before. If we give you the Mars Express spacecraft, what can you do? What do you want to do? And there were something like 10 different ideas. And the idea who won, who was selected at the end in the process, as mentioned before, was Venus Express. So Venus Express is really almost a copy of Mars Express with some slight differences because the planets are different. But we have a similar instrumentation. In fact, some of the instruments are the same on Mars Express and Venus Express. We added a few more on Venus Express, and we removed a few also. But basically, it's a kind of replica of Mars Express to study Venus. And that was very cheap because if you reuse things, it's cheaper. So we had a new mission for a very reasonable price. So that was the launch in 2005. And the main idea of going to Venus is that when you study Venus, you see that, in fact, for many aspects, Venus and Venus and Earth, they are very similar. First, they are close to each other in the solar system. I mean, Venus is just the planet closer to the Sun. But also in terms of size, mass, it's almost the same. So it's kind of sister planet. And as you know, the conditions at Venus are quite different in terms of atmosphere, temperature, pressure. I mean, it's just not possible to live on the surface of Venus, 500 degrees, 90 bars of atmosphere. So why such similar planets have completely evolved in a different pathway? And that's important for climate changes, greenhouse effect, which is very effective at Venus. So that's why we sent the mission to Venus. And also we wanted to see whether Venus is still an active planet or not, from the volcanic point of view or not. That was one of the main questions. And I think the mission was really a great success. So we were talking about disintegration of a satellite in the atmosphere. This is what happened for Venus Express, because at the end of the mission, given the trajectory, last year, in fact, exactly a year ago, Venus Express ended this mission by going into the atmosphere, and it burned into the atmosphere. We could not maintain the orbit outside the atmosphere. Celestial mechanics, gravity made that the spacecraft unfortunately ended this mission into the atmosphere. But still, so finite mission in time, but quite successful. In particular, it's a bit busy plot, but I think the most interesting result of the mission, and I think that's, if you want to remember one result of Venus Express, is this one, is evidence for active volcanoes on Venus. It's always interesting to see if a planet is active. And Venus was known to have many volcanoes, because from previous mission we got a mapping of the surface, in particular with radar from NASA missions. And we find many volcanic activities. And we find few craters. That means, again, the surface is quite young. That means there were a lot of intense volcanic activities, maybe 1 billion years ago, that spread lava all above the surface. And we cannot see what happened in the history of Venus before 1 billion years. So a lot of volcanic activities, and the question is Venus still an active planet? Do we have still a volcanic eruption on Venus? And that was one of the questions of Venus Express. And that's a bit complicated to explain, but basically we had some camera which measure the infrared radiation coming from the surface. And from this infrared radiation, you can guess the temperature of the surface. And of course, what we wanted to measure is a hot spot, which will be evidence for lava flows. And in fact, these are the measurements. So the color, they indicate the emission of the surface in the infrared wavelengths. And here, that means the spots here indicate that some hot spot of something like 800 or 1000 Kelvin or degrees were discovered on the surface of Venus. And they were identified in the volcanic region that we know from previous mapping. So I think that's quite interesting. So hot spot. Of course, there is a kind of ambiguity because we cannot be sure at the same time that it's we cannot know the size of the spot and the temperature. It's a combined information, unfortunately. So it can be a very hot spot, very small, or it can be a diffuse spot, no, not so warm. But from what we think, hot spot of about 800 degrees have been identified. So that's, I think, the most interesting aspect of the mission. There are some other measurements that from infrared radiation you can also get an idea of the age of the surface. It's a bit complicated, but really at the same time as volcanoes have been identified on the planet, we find that the age of the lava flow is quite young. Here it's written 2.5 million years. So that means, again, as if you remember what I said for Mars, 2.5 million years for a lava flow, it's like yesterday. So that means yesterday there were some active volcanoes on Venus, and so Venus is probably still an active planet. So then, and that is a very, very important result. And a complementary information is this curve in the atmosphere, that as a function of time. So here we are 2010 for Venus Express, and that's the SO2, and SO2 abundance in the atmosphere. And SO2 is a volcanic gas, and we find that there are some difference in SO2 density. So that means it's a complementary information to say that probably there are still some volcanic activity, so to say, in the Venus at the moment. So that's, I think, it's a very important result that I wanted to tell you. So that could be an image of Venus. Now it will be too much to say, but at least a few million years ago, and certainly less than 1 billion years ago, that could be an image of Venus. And when I say that the planet evolved, it's important to realize that what we see now is what looks like a quiet planet, but we could have such activity not so long ago in terms of geological scale. So I come back to this plot of the solar system that I've shown at the beginning, just to tell that I think it's really the golden age since the last 10 years or 15 years, and I think it will continue the golden age for planetary exploration. So I think you are very lucky to be in that phase, because there is plenty of data from already past and current missions. So even with the data that is in the archive, you can spend all your life digging the data and try to find new stuff. And in addition, there are always missions in the planning, like Bepi Colombo, JUICE in my case. So that will open a rich field of investigation that is almost unlimited. So I hope you can continue to be involved in that, because I think it's quite fascinating. I mean, in my case, every day I am fascinated and not bored and find new stuff. And I hope it will be the case for you, and that you might be also involved in calls for future mission, because I think it's good also to be proactive, to give new ideas, because we need ideas. The ideas come from you, from the scientific community, and then we try to best implement them and to get all the results. But it's come from you, and so I hope you can continue to work in that field. So I think I will stop now. It's good if I take questions, and thank you for your attention.